Okay, so we're back, and in this lesson we're going to continue on our discussion about trigonometry. And in the past we were talking about how to do trigonometry in right-angled triangles, and then how to apply trigonometry, the law of sines, cosines, and tangents, for non-right-angled triangles, in fact for any triangle at all. But what happens if you're stuck with an angle greater than 180 degrees? Because if you think about it, a triangle has a total internal angles of a triangle, total 180 degrees, right, Heather?
Yep.
Exactly. So if the total internal angles total 180 degrees, then you can't have an angle, like no matter how big an angle is in your triangle, none of them can be greater than 180 degrees if they all have to add up to 180. That means you can't, for instance, using the methods we've already shown, find out what sine of, say, 270 is, or cosine of 359 in degrees. This can't be done using the methods we've already talked about. So maybe there's another method, another way of looking at sine, cosine, and tangent, so that this is possible. Well, turns out that this is possible. You can figure out sine, cosine, and tangent of any angle. To do this, you'd have to understand a couple concepts about mathematics. The first is, this is a standard Cartesian plane. What that means is there's two axes, the y-axis vertically, the x-axis horizontally. Right? I'm sure you've seen this before.
Mm-hmm.
Excellent. So, what's important to know is that what the quadrants are called. So quadrant 1, or quadrant I, Roman numeral I, is up here. Quadrant 2, or II, is in the top left. Quadrant triple I is in the bottom left. And finally, quadrant IV, or quadrant 4, is in the bottom right. So it's important to keep this in mind, where each quadrant is located. Because the concept is, when you start rotating, you'll start along the positive x-axis, so going that way. And as you rotate, as you put an angle, you're rotating counterclockwise through the quadrants, like that. So far, so good? That makes sense?
Yep.
Excellent. So let's say we wanted, erase all ink on slide. Let's say we wanted to get the sine of 30 degrees. Well, you'd say, here's a triangle, right? A right-angled triangle. This length here is 1. The hypotenuse of the right-angled triangle is 1. This angle here is 30. This angle here is 60. You can't see that, but anyway, that angle there is 60. And you can therefore, using the law of sines, for instance, say something like, well, we don't know what this side's length is, and we don't know what this side's length is. But we do know that we can say, use the law of sines that we talked about earlier, that we were talking about for any triangle, and say something like, okay, well, if we label the first unknown side A, and the second unknown side B, then we can determine that sine of 30 is going to be something, let's say, well, we know that 1 divided by sine 90, because that's the length of one side and the opposite angle, equals the unknown, so that we'll call that A, side A, over sine 30. Because, of course, that's the law of sines. If you remember. Do you remember that, Heather?
I do.
Excellent. So if you work this all out, you can say that A equals sine 30 divided by sine 90. And if memory serves, sine 30 is 0.5, sine 90 is 1. So A is going to be 0.5 units in length. And I'm just going to, grab my calculator and make sure that's right, so I'm not passing along misinformation. And yes, that is correct. So as you can see, you can find the length of the vertical side as 0.5 now. Now let's say we wanted the length of the horizontal side.
Okay.
Well, you can do that once again using the law of sines, or you can use the
Pythagorean.
Thank you. I can speak English, really. The Pythagorean theorem. So, 1 squared minus 0.5 squared equals b squared. Because, of course, 0.5 squared plus b squared is 1 squared. Now, 1 squared is 1, 0.5 squared is 0.25, so that's b squared. So 0.75 is equal to b squared. So 3/4 is b squared, of course, and therefore b is root 3 divided by 2 is equal to b. So there we go. We know what b is. We know that a was 0.5. So we found out, well, sine of 30 and sine of 60 quite easily. Because sine of 30 obviously corresponds to the vertical side, the length of the vertical side. And sine of 60 corresponds to the length of the horizontal side. Because we can do SOHCAHTOA, or we can do the law of sines. So that's great when we're working in quadrant 1. But what happens when we're working in quadrant 2 or 3? Well, you start off doing the same thing. So I'm going to make another right angled triangle. I'm making it bigger this time. Here's a right angled triangle. And once again, I'm going to say that whatever length the hypotenuse is, that's 1. I don't know what length what that actually is. I don't know what scale I'll need for that to be true. But I'm saying that's how I'm constructing it. And it's a right angled triangle. And once again, it's going to be a 30, 60, 90 triangle. So we already know that this length here is 0.5, and this length here was root 3 over 2, right? Because that doesn't change.
Yep.
But here's the interesting part. If we want 30 degrees like that, as I said before, you have to rotate counterclockwise. And if a total revolution, one total complete turn, is 360 degrees, then a quarter of the turn is how much, Heather?
Oh, it's... Oh, is it 120? No.
No. A quarter of a rotation. A total rotation is 360 degrees.
360? I have no idea.
Well, a quarter of a rotation would be 360 divided by 4, which is 90 degrees.
Dang it.
So that would mean a half a rotation would be twice that, or 180 degrees. Is half the rotation. Well, we want 30 less than half the rotation. So we want 30 less than 180, which would be 150 degrees. So now we know this. Sine of 150 is the vertical value, 0.5, and cosine of 30, or sine of 60, is root 3 over 2. But then you might be curious, how is this any different than the earlier one, right? I mean, we got the same numbers the first time. Yeah. Does this mean that sine of 150 equals sine of 30? Question mark, we're not sure. And does it mean that cos of 150 equals, question mark, we're not sure, cos of 30? Well, the answer is yes and no. What's important to realize is that a point in a quadrant has an x value and a y value. The x value corresponds to the cosine of your angle, and the y value to the sine of your angle. So if you're in quadrant 2, like we're here, then you know you're going to be in positive in y, but negative in x, right?
Mm-hmm.
So, in other words, cosine of 150 is actually the negative of cosine of 30. So if you do it like that, negative cos 50 equals cos 30, that's true. And sine of 150 equals sine of 30, that's true. So I'm sure everyone's really confused right now. They're thinking, well, how did he know that? He went kind of quick, I'm kind of iffy. Well, here's the concept. in the x-axis, when you go along the x-axis, moving along positive x. When you go along the y-axis, you're going in positive y. So if you're in quadrant 1, if you have a point over here, then you know that point is going to be positive in x and positive in y.
Mm-hmm.
If you have a point in this quadrant, quadrant 2, it's going to be negative in x, because you're going along the negative x-axis. But, oh wow, that's a little weird notation. I should stay consistent, I'm sorry. You're going to have negative in x, but you're still going to have positive in y. So, wow, I'm jumping between notation. Oh well, I'm sure you guys are getting the hint of it. Negative in x and positive in y. In quadrant 3, negative in x and negative in y. And in quadrant 4, positive in x and negative in y. So say a point right there. So the concept is, since x comma y corresponds to cos comma sine, then it's really simple. Quadrant 1, if you've got an angle here, then both cos and sine are positive. Quadrant 2, say you have an angle here. Now, cos is negative, but sine is positive.
Okay.
What would happen in quadrant 3, Heather?
Be negative?
Pardon?
Negative?
Which one?
Oh, I don't know. Cos?
Okay, and what would happen to sine?
It'd be negative?
Yeah, they're both negative in quadrant 3, because as you can see, you're negative in x, negative in y, so that means you're going to have a negative value for cos and a negative value for sine. And finally, in quadrant 4, if you had some angle, it would be positive in cos and negative in sine.
Okay.
So now that we know what happens in each quadrant, how do we know what angles correspond to each quadrant? Well, you can think of quadrant 1 as 0 to 90. So quadrant 1 is 0 degrees to 90 degrees. Quadrant 2 is 90 degrees to 180 degrees. Quadrant 3 is 180 degrees until 270 degrees. And finally, quadrant 4 is 270 degrees until 360 degrees. And of course, if you go, let's say, 365 degrees, it's the same thing as only going 5, so you'd be back in quadrant 1. Or if you went, let's say, negative 10 degrees of rotation, you're going in the opposite direction, so now you'd be in quadrant 4.
Okay.
Do you follow so far, Heather?
Yeah.
No questions?
No. Positive. Negative. There you go.
Excellent. So once again, a counterclockwise rotation is a positive rotation.
Yep.
A clockwise rotation is a negative rotation.
Mm-hmm.
Okay. So if all seems pretty clear with that, then here's the concept. Let's say you wanted to have a trick to remember what sine, cosine, tangent, or all of them are positive in which quadrant. Well, here's what I like to do. Everything is positive in quadrant 1. And then, so that's only sine in quadrant 2, tangent in quadrant 3, and cosine in quadrant 4. So I remember something along the lines of, all students take calculus. Or you can come up with your own acronym. Do you have an acronym that you would use?
What's the A stand for?
Everything is positive
Okay.
in that quadrant.
Alright.
So sine, cosine, and tangent would all give you a positive value. So what would your acronym be, for instance, Heather?
Yours is pretty good.
Let's say you have to come up with your own.
Let's see. All sodas taste corny. I don't know.
Okay, perfect.
No, it's horrible. Okay.
So as you can see, you just come up with whatever acronym you can remember, and then you know which one or of the trigonometric functions, or all of them, are positive in which quadrant. Of course, the one thing I didn't really explain yet is why tangent is positive in quadrant 3. Well, it's really quite simple. We know that sine of some angle in quadrant 3 is less than 0. Or I should say less than or equal to 0. Cosine is less than or equal to 0. Because they're both going to be negative values. Well, if sine is negative and cos is negative, you may recall that tan is equal to sine over cos.
Mm-hmm.
So negative over negative gives positive. And that's why tan is positive in that quadrant.
Okay.
So now we're going to give another example, and we're going to have Heather solve it. So, best of luck. And here goes. I'm going to give you... So here's a right triangle. As you can see, you always start at the origin, draw a line, and then you go vertically from where your line segment ends to the x-axis, either upwards or downwards, to form the right triangle. So, as you can see, with the axis, that forms a right triangle. We have an angle here. Well, what angle would you like, Heather?
90.
That can't be 90.
2.
It's not drawn to scale, clearly. 2 degrees. And therefore, you know that this angle is...
What?
Well, this is 90, and that's 2. And they have to add up to 180.
Okay.
What's this angle here?
Oh. Larger than 2. Let's see.
It's larger than 2. It's smaller than 90.
Oh, and it all has to equal 180. It's 88.
Exactly, 88 degrees. Okay, so like I said, this is not drawn to scale. So what you always do is you say, okay, my hypotenuse is 1. You set that as your standard. And now, I want you to find the cosine of 2. Feel free to use a calculator, if you'd like. So,
Okay, cosine of 2.
Do you recall what I did the first time as I used the law of sines?
It's all sines.
But now I'm asking for the cosine of 2. Do you remember some relationship that we talked about in a previous lesson to relate a sine of one angle to the cosine of another?
No.
Okay. Well, maybe it'll help if I reminded you of this relationship.
It'd be nice.
Sine of some angle is equal to cosine of 90 minus that angle.
Okay.
So I'm asking for the cosine of 2.
Okay. Yeah. Let's see. Okay. Don't know how to do it.
Okay, well, let's start slowly. Remember the law of sine says that sine of an angle divided by the opposite side will be the same for every angle. And it's appropriate opposite side. So we know the opposite side to sine of 90 is 1. So sine of 90 divided by 1. And we wanted the length of the side corresponding to the sine of 2. So we go sine of 2 over unknown length, and we solve for the question mark. And if you can see ahead, you'd see that the question mark is quite simply equal to the sine of 2.
Yeah.
And similarly, if I wanted the cosine of 2, because I was talking about sines and I have no idea why, I'd say, well, the complementary angle is 88, so I do the same thing. I do sine instead of 2, I go 88, because the cosine of one angle is the sine of the supplementary angle, And there you go. I'm not sure what the answer is, but I'll say it's close to 1. It's probably going to be like...
It's 0.034.
Of 88?
No, of 2, though.
Right, because I said sine of 2, but when originally I said cosine of 2.
Yeah, you're right. It's 0.9.
Right. So sine of 88 is 0.999, etc. So 0.999. So you might be catching on to something. In both examples I've given so far, the sine of, let's say, 2 is equal to the length of the opposite side, here. Or the cosine of 2 is equal to this side's length. So maybe there's a reason for that. Maybe there's a pattern going on. Well, it turns out there is. Let's say I had really, really good artistically drawing skills. And 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Essentially, I'm drawing points 8 units from the origin on all the axes. Okay. Now, granted, this isn't looking very good and look very circular, but suppose it was a perfect circle. So, imagine. I know it kind of looks kind of oval, and it's very possible I put the points in the wrong spot. But imagine this was extremely and perfectly circular. So not like weird egg shape. Right. Perfect circle. As you can see, the points of interception are... I'm making my scale according. So I want this point of interception to be 0, 1. This point of interception here to be 1, 0. Down here, 0, -1. And finally here, -1, 0. So it's a circle, and so far so good. Do you follow?
Yeah.
Excellent. So, and then of course that's the origin at 0, 0. Well, here's the concept. If you have a circle, then, and you did the whole right-angled triangle trick, then any hypotenuse has to have a length of 1. Because the hypotenuse is a radius of the circle. So the hypotenuse is 1, no matter where it goes. And you always have a right-angled triangle. And using this construction, right? Do you see the construction? There's a triangle in this circle. Then you have, let's say, angle alpha here and angle beta here. Well, it turns out the length here is also alpha, and the length here is also beta.
Okay.
So essentially, the length from the origin to where your triangle ends in the horizontal unit is equal to beta, which is, or rather, I shouldn't say alpha and beta. That's going to be very confusing because I'm using the same letter to represent the opposite side. Instead, I'm going to say it slightly differently. Grab the eraser tool and delta pen tool. The side here is equal to sine of beta. How's that? So you actually have a number because you can't say the length is equal to an angle. Okay. Doesn't make sense. Or you could say the length there is cosine of alpha. And you could do the same thing in the vertical. Well, it turns out if you do that, then you're going to have that every point is cosine, sine of your alpha angle. Every point on the circumference of the circle is going to be simply cosine and sine of your alpha. So if I wanted a point, I don't know, give me any point on the circle.
That one.
This one. If I wanted this point, I simply draw a right-angled triangle. The hypotenuse is 1. And then let's say this angle, I don't know, was 20 degrees or something. It's not drawn to scale. Then this point right here is quite simply cos of 20, because you're moving in the horizontal. And then sine of 20 in the vertical. So that's how you can get any point on the circumference. And clearly, if you had an angle somewhere else, you might have a negative value for cos of some angle or sine of some angle, but that would also correspond to whatever quadrant you're in.
Okay.
So this is known as the unit circle, a circle of radius 1, drawn on the Cartesian plane. So I'm gonna erase all the ink on the slide,
Yeah.
and imagine the circle is still there, because if I drew it again, it would look even more sickening than the first time. Well, do you know the formula for a circle centered at the origin?
No.
Okay, well, the circle centered at an origin, or the origin, is simply x squared plus y squared equals r squared.
Okay.
R squared being the radius,
Yep.
or the radius squared. Well, we know the radius is 1. So we have x squared plus y squared equals 1. Because 1 and then 1 squared is still 1. Now, we also knew something else. We said that the amount you're moving in x is always equivalent to cosine of your angle. So cosine of theta, theta being any angle, squared, plus sine of any angle, squared, meaning you're using the same angle for both cos and sine, will equal 1. Do you see that?
Yeah.
So do you see why that happens, though?
No. I see it, though.
Okay, well, let's try this again. We have the unit circle. So I'll erase all the ink on the slide. And I'm going to end up having to redraw it. So, unit, wow, super non-circular.
It's close enough.
There's your unit circle. The radius is 1, no matter where you draw it.
Yep.
So tell me where you want the radius to end up.
Like in a quadrant?
Yeah, which quadrant?
2.
You want it to end up in quadrant 2. So here's your radius of length 1. Now here's an angle. Let's say this angle is, 15 degrees. Well, 15 degrees, as it's drawn here, is really 180 minus 15 degrees, right?
Okay.
Because you want to rotate from here to there.
Yeah.
So that's going to be 180 minus 15 is like 165 degrees. Right? So far so good, you follow?
I'm following.
Excellent. So now we know that this point here, by our construction, is going to be cosine of 165 in for x, and sine of 165 for y. So far so good?
I'm getting it.
Right. So, if that point is cosine 165 and sine 165, then we know that the sine value has to be positive and the cos value has to be negative because of the quadrant.
Mm-hmm.
The x value would be negative and the y value would be positive. But we also know that cos of 165 squared plus sine of 165 squared is equal to the radius of the circle squared, which is 1 squared. Another way to think about it is to think about it like a right-angled triangle. If cos represents the horizontal motion and sine represents the vertical motion, then a right-angled triangle states that the amount you move in each of the legs, so horizontal squared plus vertical squared, right, equals the hypotenuse squared, which is exactly what I'm saying here. Horizontal, vertical, hypotenuse. But the concept is, the important thing, the reason it's important to remember is that this works for any angle. So if I said sine of, I don't know, give me an angle.
5.
5. So sine of 5 squared plus cosine of 5 squared is going to give you 1. It's a very handy identity to know.
Okay.
So that's how you can extend your trigonometric identities to any quadrant. The concept is you build the unit circle, and from there you can say, well, look, I know an angle that I want to rotate because I know what angle I have right at the from the origin across the x-axis and then upwards along the diagonal. I know what angle forms there. In this case, we had 15 degrees. I know which quadrant it's in, so I can find out how much rotation I actually need from the origin. Well, not the origin, but from how when you start rotating along the positive x-axis.
Yeah.
I know how far I need to rotate in that sense. And therefore, I know what sine cos is supposed to have, and what sine meaning positive or negative cos is going to have. And the same thing, I know if sine, the actual trigonometric function, is going to be positive or negative. But not only that, I know the exact measurements of the sides of the triangle too. So that's what you have to realize.
Okay.
Do you follow all that so far?
Yeah. What is this all used for? No.
This helps to build up to all the trigonometric identities you're going to be seeing.
Alright.
So, the main trigonometric identity, the one you come across most often, is this one. Sine of theta. And if you want to go sine of theta all squared, people often put the square there. Simply because that way you don't read it as theta squared, but the sine itself is squared.
Okay. Can you do that in the calculator too?
In the calculator, generally the button isn't there. What you have to be very careful of is,
Alright.
on the calculator, you have to be careful to do it like this. Cosine of theta, do that part first, then square it. It means the exact same thing. Equals 1.
Okay.
So far, so good?
So far, so good.
Right. Well, it turns out that from this you can derive other trigonometric identities. For example, say I divide everything by cosine of theta and all that squared. And then, of course, I do the same thing on this side. Cosine squared of theta. Well, then what happens, Heather?
Everything's divided?
Right, but what does that mean? Like, if I would work this out, I'd get sine of theta divided by cos of theta. All of that squared. Do you know what that is? Sine of theta divided by cos of theta? Do you remember?
No.
Well, that was tangent of theta. We were talking about that.
Oh, yeah, tangent.
So tangent squared of theta. And then, what's cos of theta squared divided by cos of theta squared?
1?
Right. Plus 1 equals... Well, 1 divided by cosine has a very special name. It's called secant of theta squared. So secant is very simply... the easiest way to do this is to say cosine of theta. 1 divided by cosine of theta. I'm going to make a little aside here, so I'll put it in a box.
Okay.
Equals secant of theta. 1 divided by sine of theta equals cosecant of theta. And 1 divided by tan of theta is cotan of theta. So essentially they're just fancy names given for the 1 divided by. And it's the only thing to remember is that cosine becomes secant and sine becomes cosecant. And those are the 3-letter acronyms for it. So there you go. So now that we had the primary identity, sine squared plus cos squared equals 1, we managed to derive a secondary identity.
Cosine?
Pardon?
What?
Okay. We know... I'll erase all the ink on the slide and I'll rewrite this neater. We knew this because we already showed it with the circle. Right? We showed this. Do you remember that?
Mm-hmm.
So you understood how that came up?
Yeah.
Excellent. Well, then what we did is, all we did was a simple algebraic manipulation, which basically means we divided both sides of the expression by cosine of theta squared. Well, sine of theta squared divided by cosine of theta squared is tan of theta squared. And then cosine of theta squared divided by cosine of theta squared is 1. And 1 divided by cosine of theta squared is equal to, well, 1 divided by cosine, I said, was secant. So secant of theta squared. So this is just another identity. That's all this is.
Alright.
And of course, you can get other identities as well. So the important thing to get from this lesson is two things. Okay?
Okay.
The first important thing is to remember the fundamental identity. This is the one you're going to be using most often.
Okay.
The second thing that's worth remembering is the whole unit circle thing. So I'm going to erase it and just go over this one more time briefly. The unit circle is very important. What it is quite simple. You make a circle of radius 1. So we'll assume this is extremely and perfectly circular. This is better than some of the other ones I was getting, so. This is extremely and perfectly circular. And now you make a triangle in a quadrant, which is very simple. You start at the origin, draw the radius of the circle, and then draw a vertical line, connecting it to the x-axis, and you have a right angle triangle. Because our circle has a radius of 1, the hypotenuse is 1.
Okay.
And the only other thing that's worth knowing is that every point that you have can be broken down into a horizontal movement and a vertical movement. The horizontal movement, in other words, the movement in x, is simply cosine of the angle here. This angle, I'll call it alpha. Cosine of alpha. The vertical movement is sine of alpha. And that'll give you any point on the circumference of the circle. So, in this case, let's say alpha was, 15 degrees. Well, then the important thing to realize is you don't just plug in alpha directly. You have to figure out how much rotation is actually in alpha. Well, it's simply that much, which would be 360 minus 15 degrees. So you could either plug in 360 minus 15 degrees and get the proper sign for cosine and sine. It sounds very confusing, sine of cosine and sine. What I mean is you know if cosine or sine is positive or negative based on sine and cosine of 360 minus 15 degrees. Alternatively, you could just use the 15 degrees that you measured for your rotation in your triangle, for that angle. But then you'd have to use what quadrant you're in to tell which one's positive and negative. Do you see what I'm saying?
Yeah.
So, for instance, let's say I used only that 15 degrees for alpha. And I did it like this. I plugged in the alpha in both, and I didn't bother going 360 minus 15.
Mm-hmm.
So I didn't bother calculating this whole rotation that happens if you're doing regular rotation. Well, then what happens? Would cosine be positive or negative?
Negative?
No, not quite.
Okay.
Cosine represents the movement you're moving along the x-axis. So that's going in the positive direction. Cosine's positive.
Okay.
And sine would be positive or negative?
Negative.
Exactly. Because don't forget, we had that whole acronym. It was a soda acronym in your case.
Soda.
Something like, always sodas taste crappy or something like that. Was your acronym?
It's better than mine, but yeah.
No, that was yours, I think.
No, it wasn't.
Oh, what was yours?
I'll never say. Yours is better.
Oh, mine. Mine, yeah. It doesn't matter. It's whatever acronym helps you remember, whatever works as a memory aid for you. So as you can tell, in this bottom quadrant, the cosine value will be positive, but the sine value will be negative.
Okay.
And there you go. So if you could just keep these two things in mind, you're well on your way to understanding trig. So with that, that's going to wrap up this lesson. Thanks a lot, guys.